Okay, we'll talk about inverse Laplace transforms today. So we talked about Laplace transforms last time, went through the definition, using some of the properties, build up a small table of transforms and properties. So, but we're not going to use the inverse Laplace transform definition to calculate based on a contour interval. So we're going to use the partial fraction expansion method, which I think you saw in differential equations. And everyone's kind of got their own way to do this. You know, if you like what you learned in differential equations, there's some students that had in the past that were shown a way to do partial fraction expansion in there, and they like that, and that's fine. I'll show you the way I like to do it. The textbook has even a different way. So the idea is, if you look at our table, there's fairly simple rational polynomials in every case, either first order or second order polynomials. But we can write them typically as some numerator over some denominator. And if it's multiplied by an exponential s term, then that corresponds to a delay. You can write this as I1 to m of bi s to the I. So the numerators of capital M order, so it's a lowercase m, and then the denominator I1 to n ai si is of order n. And the partial fraction expansion is actually based on being able to factor these two polynomials. So we talked about the pole zero factorization last time. You can factor the numerator. If it's a fourth order polynomial, it has 4 zeros. Now the polynomials we'll work with all have real coefficients. Even though the zeros and poles may be complex, the polynomial expressions in the numerator and denominator here will all have real coefficients. It'll be like 3s squared plus 2s. We'll never have a js or anything like that. And that's a consequence of the systems that we work with. But as a consequence of that, our zeros and our poles will either be real, or if they're in the complex plane, they have to occur in conjugate pairs, complex conjugate pairs. I'll talk about what that means, but there's certain implications of that. So for example, if you had a fourth order polynomial, you could have 4 real roots. You could have 2 real roots and then a complex conjugate pair. You could have 2 complex conjugate pairs of roots, but you couldn't have 3 real roots and 1 complex root. So remember what a complex conjugate is. You know, if you've got, let's say, a 0 that's a plus jb, then the complex conjugate of that is a minus jb. So if it's a over and b up, then the complex conjugate would be at that location. So our zeros, we use O's for zeros, will always occur in complex conjugate pairs like that, as will our poles. Now, again, we could have a single 0 here on the real axis, or poles on the real axis, but if they're off the real axis, they'll always occur in pairs like that. The other way to write this, you know, is it's got some magnitude and then some phase angle. So, this is A over and B up. Let me just call the magnitude A, capital A. This is the phase angle theta. In polar form, the complex conjugate has the same magnitude, but negative angle. So, or in exponential form, I guess it's e to the j theta, e to the minus j theta. Essentially, everywhere j appears, you replace it with negative j to get the complex conjugate. So there are a couple different cases that, I don't know if you looked at all the different cases that can occur in differential equations, but we will typically require that the order of the numerator is less than the order of the denominator. That's necessary in order to use the partial fraction expansion technique. And then so if that's true, we're good to go. We're good to take the next step. We can start the partial fraction expansion. And I'll get to that in just a minute. I want to look at the other cases when this is not true. So typically, the numerator is of third order, maybe the denominator is of fourth order. That would satisfy this condition. Another case you can have is if they're of the same order, you do a little trick. You factor out Bm over An, the leading coefficients, if necessary, and do synthetic division, apply the division method. So as an example, let's say you have x of s is 2s squared plus 8s plus 6, and then s squared plus 2s plus 1. So here the numerator and denominator are of the same order. And so students will often jump in and start doing a partial fraction expansion on this. It won't work, you'll get the wrong answer. You have to, you can either, well, the first step is factor out the leading term, so I'll rewrite this as s squared plus 4s plus 3 over s squared plus 2s plus 1. And then you now need to carry out that division. Now, I've seen at least two different ways to do that. Okay. The first technique is what I've seen is called synthetic division, where this will go into that one time, s squared will go into s squared one time. So we have s squared plus 2s plus 1, and then so the remainder would be 2s plus 2. And so we can write this then as 2 times 1 plus, this is the remainder, 2s plus 2 over s squared plus 2s plus 1. Then now we can use partial fraction expansion on the rational polynomial. The other technique, hopefully we'll get the same answer, that I've seen used, that and actually a student showed me this a couple of years ago. S squared plus 2s plus 1 is just to write s squared plus 4s plus 3, add and subtract the denominator term. Plus s squared plus 2s plus 1. Doing this right? I think I'm writing it down in the wrong order. sorry. Doesn't really matter, but so add and then subtract the denominator term, 2s plus 1 plus s squared plus 4s plus 3 over s squared plus 2s plus 1. Now, okay, and remember your basic rules of fractions, like 1 over 2 plus 1 over 3 is not 1/5, right? That's not correct, but I know it's been a long time since you probably worked with fractions. But here you can split up the numerator. Here we've got 1, and then now the s squared terms will cancel. What I'm left with is 2s, and then 3 minus 1 plus 2, s squared plus 2s plus 1. So you get the same result, but you don't have to actually do the division. Just add and subtract the denominator. Is that clear what I did there? It's just a trick. Yes, no?
Yes.
Yes, okay. So either technique there. The third case we have to deal with is if the numerator is greater than the denominator, you factor out not only the leading constant term, bm over am, and s of m minus m. So again, it's easier to illustrate with an example. So we've got x of s is 6s cubed plus 4s squared plus 8s plus 6 over s squared plus 2s plus 1. I can write this as, I really want to get another s term in the denominator. So I can multiply and divide by s. I'm also going to factoring out this numerator term. So I'll have s cubed plus, I want to write that. I wrote it wrong. 4/6s squared plus 8/6s plus 1. And then this would be s cubed plus 2s squared plus s. Now I can do the synthetic division on the second term. I'll have I don't want to carry that out, but I'll get a 1 plus, again, a rational polynomial that I can then do synthetic division on, or partial fraction expansion on. So let's look at doing partial fraction expansion with a couple of examples. And there are 3 different cases we have to look at. One is where we factor and get real poles. And then the other case is where we get repeated real poles. And then a third case is where we get actually a complex conjugate pair of poles. So distinct real poles. And this is by far the easiest case. So here, we factor the denominator into its poles. And in the partial fraction expansion, you can write this as, again, this, I'm assuming here that in this case, I've written a second order denominator, that the numerator is of first order or a constant. Again, that's required to do the partial fraction expansion. So two tricks are involved. One is you've got to factor the denominator into its poles. And then the second part of the problem is to find those constants that are in the numerator. The second case is repeated real poles. So when you have the distinct real poles, you have constants in all the numerator terms. With repeated real poles, and over S, say you get a S minus P to the M, then you have a constant term over, but it's S minus P to the M, S minus P to the M minus 1, plus so on and so forth, down to B1 over S minus P. So this is a mth order pole at the same location. But the partial fraction expansion then looks like this for that case, the repeated pole. Again, the hard part here is determining those numerator coefficients. Okay, that's the next step we'll take. And then the distinct complex poles. And S. So S minus P, S minus P conjugate. Now, you can actually treat this like the first case, where you've got distinct poles at P and its complex conjugate location. That leads to complex constants in the numerator. So the approach I prefer is actually just complete the square in the denominator, and we'll go through this, how to do that. Okay. So leave it as a second order term. Now in the partial fraction expansion, though, that means what you'll have in the numerator is a polynomial of 1 degree lower. And the trick there is finding the C1 and C2 constants. So let's look at an example. And typically, you may have in a problem, you may have distinct real poles, you may have repeated real pole, you may have complex poles, all in the same nasty denominator polynomial. So, example, this is problem 313b. So, from the book, so it was 4, and so here, 2 in this problem, the denominator was already given in factored form. If we multiplied this out, it would be a third order polynomial in S, and you'd have to find the roots. Now, Octave will do that for you, or in many cases, your calculator will do that. I kind of expect you to know how to factor a second order polynomial. You can use the quadratic equation to do that, but I won't require you to at least analytically factor a third order or higher polynomial. Sometimes you just turn to Octave or Wolfram Alpha and ask it to find the roots for you. But the factorization here is A1 over S plus 1. We've got a distinct pole at S equal minus 1. And then I would have an A2 over S plus 2 squared and an A3 over S plus 2. Because we have a repeated real pole at s equal minus 2. Now, the pole 0 plot, there are no zeros. I've got a constant in the numerator, so there are no zeros. But I would have a single pole at -1. It's s equal -1. You can get the pole directly from the factored form. Causes the denominator to be 0. And then at s equal to -2, I would have a double pole. Because I have the s minus 2 squared term, or s minus 2 times s minus 2. So the pole 0 plot would look like this. That's really unrelated to the partial fraction expansion. But, so, getting the coefficients of the distinct real poles is easy. So, you use what's called either the residue method or the cover-up method. So what we essentially do is multiply through by s plus 1. And if we do that, I'm not going to rewrite it because there's a trick to doing that. If we multiply both sides by s plus 1, it cancels over here, right? It would cancel here and I would just leave it. I would just have a1. But here I would have a2 times s plus 1. And here I'd have a3 times s plus 1. Then I let s equal -1. Again, I don't have an s, I don't have this term here. Or here, I have an s plus 1 multiplying here, but when I let s equal -1, this is 0. And that's 0. So it's called the cover-up method because what I do is a1 is simply x2 of s, mathematically, we can write it like this, times x plus 1, evaluated at the pole location. Okay. So that was the math behind that. But in practice, all I have to do is cover up that pole term on the left-hand side here and evaluate what's left at s equal to -1. -1 plus 2 is 1, 1 squared is 1, and so a1 is equal to 4. You probably learned something like that in differential equations. Have you did? We can actually get the a2 term the same way. So the term for the highest order one here, the others are more difficult. But the same trick works for a2. It's x2 of s times s plus 2 squared. Now we evaluate at the pole location s equal -2. Again, the same trick would work when we multiply through by s plus 2 squared. That term goes away. Here we're going to let s equal -2. This term would be 0. Here we're left with a2. Here we would still be left with an s plus 2 because I'm multiplying through by s plus 2 squared. But then this term would go away when I let s equal -2. So then I can get this one easy, cover up that term, let s equal -2. I will then have 4 divided by -1. So that's a -4. Okay. Unfortunately, the third term is a little more difficult. Now in the book, he talks about there's a way to actually take the, do this multiplication, take the derivatives of both sides. I typically just use what's called the polynomial method, where I just multiply both sides by the denominator. I know a1 and a2, so the trick is find all the constants you can using the cover-up method. So in the polynomial method, now there's some other tricks. You can just let s equal anything at this point. You can let s equal 0. Can't let it equal a pole term. But if I let s equal 0, here what am I going to have? 4 over 4. I'll have 1. I'm going to have a1 over 1. Well, I know a1, it's 4. I know a2, The only unknown in that equation would be A3. So we'll use that technique in just a second to verify that we get the same result. But in the polynomial method, I multiply both sides by the denominator, and I end up with this equation, A1 times S plus 2 squared plus, and actually, I'm going to go ahead and plug in A1 because I've got 4. I've got A2 is minus 4. Now, when I multiply this by S plus 1 times S plus 2 squared, I'm just left with S1, yeah, just S1. And the last one, it's got the one I'm trying to find, I'll have an S plus 1 times S plus 2. Okay. Is that okay? Now, in the polynomial method, the highest order S term I'm going to have here is an S squared term. I can tell that by looking at it. So what I do is on both sides, I equate just the S squared coefficients. I don't have an S squared coefficient on the left-hand side. I have one here, but I don't really have to multiply that out. S plus 2 squared is S squared plus 4S plus 4, right? But I'm really just equating the S squared term, so I can tell that that's going to be a 4. There is no S squared term here. I get one here, right? That coefficient is just going to be A3. Okay. So that tells me A3 is equal to minus 4. So I think this is usually a lot simpler than the derivative methods that they often teach you in differential equations or something like that. You could actually, I could have started with, you can actually use this method to get all 3 coefficients. So we can do the same thing with the S coefficients. And there is no S term here. Now, here it gets a little trickier. You know, the S term here, when I expand that out, is going to be 4S times 4. That's going to be 16. Here I do have an S term now. It's 4. And then the S term here is going to be 2S plus S, 3S times A3. But hopefully this works out. 16 minus 4, 3 times A3 is minus 12. 16 minus 4 minus 12 is 0. So it checks out. So I could have used this one to actually solve for A3. And then finally, the constant term is, I do have a constant term on, or the S to the 0 term. I do have a constant term. I have a constant term here. 2 squared is 4 times 4 is 16. Here I'll have minus 4. The constant term there is going to be 2 times A3. So I'll have 16 minus 4 minus 8. I screwed up somewhere. A3 is minus 4, right? Do this right? No, I didn't. I was thinking this was 0 over here, but it's 4. 4 is equal to 16 minus 4 minus 8. So yeah, that checks out. The other method, once we have A1 and A2 that you could use, is just let S be anything. So let me go back up here and pretend we don't know A3 yet. You can't pick one of the pole values because everything blows up. So you usually pick like S equals 0, S equal 1, S equal minus 1, as long as they're not poles. But if we let S equal 0, I'll have 4 over 1 times 2 squared. I'll have 4 over 4 on the left. I'll have A1, which I've already found. And then I'll have A2 over 4. But A2 was minus 4. So minus 4 over 4 is minus 1. And then here I'll have A3 over 2, right? So solving for A3, here I'll have what, that's a -3, bring that over. That's 3, can't do math. That's 3, subtract 3, I'll have -2. A3 would then be -2 times 2, solving that, which is -4. Then you could use that technique too to find all 3 coefficients. Just plug in 3 different values for s. You can't use s equal -1 or s equal -2 though, because those are pole terms. But I could use s equals 0, get one expression involving the 3 unknown coefficients. Let s equal 1, not -1, but 1. Let s equal 2. You could let s equal pi or 0.5 or whatever. So then you'll get 3 equations and 3 unknowns, okay, that you have to solve. That's often not easy. So the recommendation is use the cover-up method to get all the terms you can, and then by hook or crook, find the rest of the coefficients. And I usually prefer this polynomial method. Okay, so we're not done, but we do have a partial fraction expansion now. So we know at this point, x2 of s is 4 over s plus 1. We have -4 over s plus 2 squared. And I have -4 over s plus 2. Did I copy all this down right? But now, hopefully, we've got terms that are simple enough to be found in our table. Something over an s plus 1, that's an exponential term. Okay, so that's actually early on in our table. That's Laplace transform pair 3, okay, which is 1 over s plus a. So I have here x2 of t. Transforming these back, this is going to be 4 e to the minus t u of t. That's this first term. The last term is also an exponential term, but go ahead and do the middle term. The middle term is pair 6, 1 over s plus a squared. So that's going to be -4 t e to the minus 2t u of t. And then finally, the last term is -4 e to the minus 2t u of t. We can make that, we can factor out the 4 and the u of t, make it look a little prettier, but that's going to be the final result. Any questions about that? Okay, we'll do one more example, and we'll probably be out of time, but if not, I won't hold you late on Friday. You might get out a little early. I want to take a look at what do we do with the complex poles. The complex poles become sine and cosine terms if they're on the imaginary axis. If they're off the imaginary axis, if they're to the left of the imaginary axis, they become exponentials, decaying exponentials times cosines and sines. If they're on the right side, they become increasing exponentials times sines and cosines. But, so, x of s is s plus 20, s squared plus 6s plus 10. Okay. Now, first thing you want to ask yourself is the numerator of lower order than the denominator? The answer is yes. The denominator is third order, the numerator is a first order polynomial in s. Second thing you want to ask yourself, I guess, is does this thing have real roots or complex roots? b squared minus 4ac, right? That's the part that goes under the radical. 36 minus 40. I'm going to have square root of minus 4. So it's got complex roots. So the way I handle that is we can do this, a1 over s, plus, I'm going to leave this s squared. We'll come back to this in just a minute, plus 10. But now it's not just that because this is a second order polynomial, it's not just a constant in the numerator, it's a first order polynomial. So I'm going to just call those A2 and A3. And we'll show you how to handle that term. But first we get A1, that's the easy one. So how do I find A1? It corresponds to a pole at the origin. Just cover up the S term and let S be 0. So I'm going to get 20 over 10, and A1 is 2. Is that okay? So A1 is equal to 2. And then usually what I do then is the polynomial method again. I just like that. And here you could plug in s equal 1, s equal minus 1, those aren't poles. I can't use s equals 0 because that is a pole, and then get two equations. But polynomial method, so multiply through by the denominator, and then I get 2s squared plus 6s plus 10, and then I get plus A2s plus A3 times s. The highest order term on either side is an s squared. Usually it's easiest to use the highest order term and then the constant term, because then you don't have to worry then you don't have to worry about here, where we get these inner terms. The constant term and the highest order term are usually much easier to determine. S squared, there is no s squared coefficient on the left. So 0 there. What's the s squared coefficient here? 2. What's the s squared coefficient here? A2. So I get A2 is minus 2. Now again, we could do we might as well. Actually, it looks pretty easy here because I don't have to expand anything. I do have an s to the first power term on the left. It's 1. Here, my s coefficient is 12. And here, my s coefficient is A3. So that gives me A3 is equal to minus 11. And just as a check for my constant term, I'll have 20 is equal to 20. Because there is no constant term here. So it gives me a little confidence that all this has worked out. So now what we have for x of s is 2 over s, and then I have minus 2s minus 11 over s squared plus 6s plus 10. Let me just pull out the minus sign there. We'll come back and tackle that. What's the inverse Laplace transform of 2 over s? 2 u of t, right? So I know I've got that term. So, you know, x of t over here. X of t is going to have a 2u of t minus the inverse Laplace transform of this guy. So let's take a look at it. And then, because it has these complex roots, we're not actually going to factor, we're just going to complete the square here on the denominator. So you write that as s plus 3 squared. It's half of this, the s term, the coefficient times the s. Because this will give me s squared, when I multiply this out, I'll get s squared plus 6s plus 9, right? That's what this is equal to. Well, here I've got s squared plus 6s plus 10, so I have to add 1. Now, if you look, the reason I'm doing it this way, if you look in your table, and all these sines and cosine terms, you look at 13 and 14, both kind of have that, right? S plus a squared plus omega 0 squared. Now, I could write that as 1 or 1 squared. And sometimes you might get a 3, but you could write that as square root of 3 squared, something like that. So this is in that form in the denominator. In the numerator here, I've got, you know, 2s plus 11, which is close to 14. You know, 14 in the denominator, it's got s plus 3 squared plus 1 squared. I really need an s plus 3 in the numerator here, right? So this is where we have to use a little algebraic trick, but again, I'm going to force an s plus 3. That would be 6. And then you always have to make sure you maintain the equivalence. So 2s, 2 plus 3 is 6, plus 5 is my 11. Now I'm almost there. Now that I've got the s plus 3 there, I can split this now. Plus a constant term, which would be 5 over that. I'm going to pull the 5 out. And have 1 over s plus 3 squared plus 1 squared. This matches 14 now, right? It's 2 times really pair 14. This matches 13, the sine term. Now, when I factor out the 5 here, what if I had a 2 squared here? I could have had a 2 up here and then pull out a 5 half, you know, some other trick like that to get that constant term there. But now this becomes the inverse Laplace transform of all of this then. S squared plus 6s plus 10. And these are the nasty ones, but this becomes 2. This was the cosine term, e to the minus 3t cosine of t u of t. Okay, that's that term. And then this is the sine term, 5 e to the minus 3t sine of t u of t. I could have actually used pair 15b and not even had to worry with all of this. If you see 15b, it's got an as plus b, kind of a more general. there's some nasty looking formulas there, and it reduces to just a cosine. Let me take do one more step with this though. So this Laplace transform is equal to, let me factor out an e to the minus 3t u of t. Cosine t, sorry, 2 cosine t plus 5 sine t. Those are two sinusoids at the same frequency, so they can be combined. You can probably find a trig identity for it. I always use phasors. 2 cosine t. You have to use phasors. You have to write the sine as a cosine. But a cosine shifted to the right by 90 degrees is a sine. In phasor land, this is 2 at an angle 0, or just 2. This is 5 at an angle of negative 90. Okay. Or 5 at an angle of negative 90 is minus J5. Right? If someone has a calculator and can tell me what 2 minus J5 is in polar form, we can go home. Magnitude is going to be the square root of the sum of squares of 4 and 5, right? So it'd be square root of 29 is the magnitude. The angle is, I guess, minus arctangent of the imaginary part over the real part. So this becomes the square root of 29 cosine of t minus the inverse tangent of 5/2. And then, don't want to forget the e to the minus 3 u of t, but then I'm done. And it's okay to leave it in this form, that's fine. But you can combine those, and typically, anytime we have sinusoids at the same frequency, we like to combine them into one sinusoid. These are equivalent. All right, have a good weekend. Well, actually, I think finally look at some circuits on Monday.
Because I'm not in it. It's boring and I gotta join the damn thing.
I'm not even a microphone.
Yeah, right.